Let's continue our discussion of L'Hopital's rule and indeterminate forms for which we can apply L'Hopital's rule. So these two indeterminate forms, we've come across one of them before, where we have this infinity minus infinity, the difference of infinity minus infinity. And that is indeterminate because we're not sure which quantity, which function is approaching infinity faster. Is there some kind of balance, right? It's always that power struggle is what we think of with an indeterminate form. So this is definitely one that we've come across before, and we've utilized some algebraic techniques to come up with ways to compute that limit. Now, another indeterminate form is 0 times infinity. And again, this is a product when we have a product of two functions, and one of those functions is approaching 0 as x approaches a, and the other function is growing without bound, approaching infinity. And that's what these two statements are saying. If we have a product where one is approaching 0, one's approaching infinity, or we have a sum or a difference where one quantity is approaching infinity and the result is infinity minus infinity. Okay? So what do we do with this? Well, and here's some examples that we're going to explore. What do we do with this? Because neither one of these is in the form that we can apply L'Hopital's rule to. L'Hopital's rule, we have to have forms, the other two forms that we've worked with, 0 over 0 or infinity over infinity. We have to have a quotient so that we can apply that L'Hopital's rule. Remembering that L'Hopital's rule says that the limit, if we have one of these forms, then that the limit as x approaches a of f of x over g of x, quick reminder, is equal to the limit as x approaches a of f prime of x over g prime of x. If we're of one of these forms, then we can apply that. That's what L'Hopital's rule says. So what do we do if we're not in one of those forms, right? Like, what do we do if we're not in the 0 over 0 or the infinity over infinity, and yet we still have something that's indeterminate? Well, what we can do is we can just use a little bit of algebraic manipulation. We can turn a multiplication into a division pretty easily. We just use the reciprocal. We can do things like pulling out common factors, finding common denominators. There's all kinds of little techniques that we can do, but we've got to get it into one of those forms. So if we have one of the other indeterminate forms, the two that we're looking at here, and we'll have a few more that we'll add as well. If we're in one of the other indeterminate forms, not the two forms that we can utilize L'Hopital's rule on, what we do is we get these forms into a form that looks like that so that we can apply L'Hopital's rule. So that's the goal, and we're going to show that with some examples. Let's get our steps for applying L'Hopital's rule up here on the board or on the screen, and let's talk about what we can do here. Okay, so this is what we worked with on the last video when we had a quotient. Well, what if we're not in a quotient? What if we're f of x times g of x? Or what if we're f of x minus g of x? Well, that's what I was just mentioning. We've got to get it into this form. So we've got to do something to get it into that form. Something algebraically to get it into this form so that we can apply. This is the form by which we can apply L'Hopital's rule. As long as this form turns into that 0 over 0 or infinity over infinity. So here's the piece that we're adding in this video. When we have these other two indeterminate forms, sometimes we have to use algebraic manipulation to put the limit into one of these forms, the 0 over 0 or the infinity over infinity. If we can get it into that form, then we can differentiate numerator and denominator separately, simplify and reevaluate the new derivative, the limit of the ratio of the two derivatives, f prime of x over g prime of x. And then we just repeat the process as necessary. So that's what we're going to do. So when we come across this example, we see that this is a product. And when I go and I take this limit, let's see what happens. So when I take the limit as x is approaching infinity of x is, of course, infinite. I'm going to grow without bound. And then when I take the limit of the tangent of 1 over x, well, 1 over infinity is going to approach 0, and then the tangent of 0 is going to be 0. Now that is indeterminate. You know, it might be useful at the top of your paper as you're working with limits to write our indeterminate forms. We have 4 of them so far. 0 over 0, infinity over infinity, infinity times 0, and infinity minus infinity. So all of these are our indeterminate forms, the forms that we've worked with up to this point and talked about being indeterminate. So those are our indeterminate forms right now. So if I come across a form like that, what I'm going to need to do is get it into a quotient of some form so that I can apply L'Hopital's rule. I'll highlight the 2 indeterminate forms that are applicable, that L'Hopital's rule is applicable with. So how am I going to do that? Well, anytime you have a product like f of x times g of x, if you want to turn a product, this little algebraic manipulation, if you want to turn a product into a quotient for whatever reason, and we have reason here so we can apply L'Hopital's rule, what you can do is you can reciprocate either one of these 2. So you could reciprocate f of x or g of x and put it in the denominator. So I'm just going to write it as f of x over 1 over g of x. But these are equivalent. These are equal. I've just algebraically manipulated these 2. Normally we like to have things simplified, so we wouldn't really want to create a fraction within a fraction, a compound fraction. But if necessary, in order to apply a rule like L'Hopital's rule, then maybe that's what we do. So this is a useful little strategy. So let's thought bubble this. This is a strategy that we can employ when we've come across a limit of indeterminate form infinity times 0. So we can come down here now and we can say, notice I am not actually taking L'Hopital's rule. I can't take L'Hopital's rule. It's not in the correct form yet. So what I can do though is I can take the tangent of 1 over x and I'm going to reciprocate the x and I'm going to put 1 over x in the bottom. Now notice when I take this limit, we've already talked about how the tangent of 1 over x is 0 because it's the tangent of 0. So this is going to be 0. And 1 over x, of course, is also 0. So notice what I've done by using this strategy. I've created a limit that is of indeterminate form by which L'Hopital's rule is valid. So now that I've justified I have the L'Hopital's rule 0 over 0, the quotient, I can jump to L'Hopital's rule. Again, my notation, since it's the first example in this video, my notation when I do apply L'Hopital's rule is to put a little LH above the equal sign. That indicates that I am using L'Hopital's rule here. And then we can take the limit as x approaches infinity. Now what I need to do is take the limit, remember, of the numerator, which will be secant. We'll have to apply chain rule here, secant squared of 1 over x, and then the derivative of 1 over x is negative 1 over x squared. So I think of this as x to the minus 1, and then I can apply power rule. So negative x to the negative 2, and then I can drop the x squared down. And then I need to take the derivative of the bottom. Again, that's 1 over x, so that's going to be a negative 1 over x squared when I take the derivative of the bottom. And notice before I go and apply the limit again, there is some definite simplification. Those 2 factors cancel. And so then this is, again, just a simplification, not taking a L'Hopital's rule here, so I have no notation on this equal sign. Limit as x is approaching infinity of just the secant squared now of 1 over x. And so now I can apply that limit. Let's see what happens. Limit of the secant squared of 1 over x. Well, 1 over x becomes 0, so this is the secant squared of 0. But the secant squared of 0 is 1, so this is 1 squared or 1. And notice that I am able to take that limit now by first identifying what the indeterminate form was. It was form infinity times 0 up here at the top. And then using some strategy right here, using some strategy so that I could get it into that form 0 over 0. This is where L'Hopital's rule can be applied. Can be applied. But I have to get it into an infinity over infinity or 0 over 0 form before I can apply L'Hopital's rule. Okay, so let's take a look at another one. So I come across a limit of 1 over x minus 1 over the sine of x as x is approaching 0 from the right. Okay, well, what's that going to be? If I were to take this limit, we are approaching 0 from the right, so we do have positive values. So 1 divided by something that is approaching 0 from the right is going to be infinite. And then I have 1 minus the sine of x, something approaching 0 from the right of the sine of x. Then this is also going to be 0 from the right, so I would be subtracting infinity. So I have infinity minus infinity. So when I do those, I get infinity minus infinity, which is a power struggle, and this is of indeterminate form. This is a power struggle because just think about it. Normally, if we were to have infinity minus a number, well, that would clearly just be infinity. But if I were to have a number minus infinity, that would clearly be negative infinity. If I were to have a number minus a number, then I would get just some other finite number, positive or negative. We'd have to figure that out. So notice, without more information, it's indeterminate. There's a power struggle here. There is, we cannot determine it without more information. Okay? Infinity minus infinity is indeterminate form. But it's not the correct form to apply L'Hopital's rule to. I need to get it into, right? I need to somehow turn this into 0 over 0 or infinity over infinity. So how am I going to do that? Well, that depends, I guess, on the function we're given. And this function was given as 2 fractions by which we could find a common denominator. So let's find a common denominator. So this is going to be x sine of x would be our common denominator. And this will need to be sine of x, and this will need to be x, and this becomes the limit. Notice I am not taking a limit, I'm not applying L'Hopital's rule, I'm simply rewriting the function to hopefully get it into a form that I can apply L'Hopital's rule to. And now I have sine of x. Now I have a quotient, sine of x minus x over x times sine of x. If I let this limit, take this limit as x is approaching 0 from the right, I'm going to get 0 minus 0, which is 0. They're both positive. And in the bottom, 0 times 0, which is 0. And notice this is a form that I can apply L'Hopital's rule to. But I've got to get it in that form. In our initial form, it was not. It was in a quotient. So now I can apply L'Hopital's rule, and I can go ahead and do so. So L'Hopital's rule... again, the little notation, I put the LH above the equal sign because I'm going to apply L'Hopital's rule. The numerator is going to be cosine of x minus 1. The denominator is a product. So see, we definitely have a product of 2 functions here. So in order to take that derivative, I will apply product rule. So I'll get 1 times the sine of x plus x times the cosine of x. And I'm looking to see not a whole lot to simplify there, so I'm going to go ahead and see what that turns out. If I allow x to go approach 0 from the right, the cosine of 0 is 1, so I get 1 minus 1. On the bottom, I get 1 times 0, so 0 plus, and now I'm going to get 0 times 1. So that's going to become 0 over 0 again. And again, that means I can repeat L'Hopital's rule because I'm once again in an indeterminate form that L'Hopital's rule is valid. So I can come here and I can say, well, let's apply L'Hopital's rule again. So now we're taking the limit as x is approaching 0 from the right. The derivative of cosine is negative sine. On the bottom, I have 2 terms here. So the derivative of sine of x is cosine of x. Here I have to apply product rule again because I have x times cosine of x. So when I apply the product rule here, this is going to be 1 times cosine of x plus x times negative sine of x. Okay, so applying product rule there, take the derivative of x, we get 1 times cosine of x plus the derivative of cosine of x, negative sine of x times x. All right, and let's just see. Let's continue. Before I evaluate this, let's simplify that just a little bit in the bottom. We've got minus sine of x on the top. On the bottom, we end up with 2 cosine of x, because we have cosine of x plus cosine of x, minus x sine of x. And now I can, once again, see what we get when we evaluate this. So we get 0 on the top. On the bottom, we get 2 times 1 minus 0. So we get 0 divided by 2. 0 divided by 2 is not indeterminate. 0 divided by 2 is determinate. That is actually equal to 0. And that gives me my answer for this limit of 0. So notice on that problem, that's a nice problem with a few different strategies. We started with an indeterminate form that was a difference, infinity minus infinity, and we manipulated it till we got it into a form that we could apply L'Hopital's rule, 0 over 0. Applied L'Hopital's rule, simplified, had to apply L'Hopital's rule again, simplified, and then ended up with a 0 over 2. 0 divided by 2 is not indeterminate. 0 divided by anything is 0. I should say 0 divided by anything other than 0. When it's 0 over 0, it's indeterminate. Okay, let's do one last example to round this out. And notice on this particular problem, we've got x times e to the 1 over x minus x, as x is growing without bound. So what happens when we evaluate this one? So when we evaluate this one, we get an infinity times e to the 0, which is 1, minus infinity. So we end up with infinity minus infinity, which is indeterminate, but not in the proper form by which I can apply L'Hopital's rule. So what do? Well, on this one, the first thing I would notice is a common factor of x. So I would pull that x out. So we're going to have the limit, so again, just manipulating a little bit here, limit as x is approaching infinity of x times e to the 1 over x minus 1. Now notice if I start right here and jump right into it, I would end up with infinity times 1 minus 1, which is infinity times 0. So what's kind of fun about this one is we're seeing all kinds of indeterminate forms. So at first, the way the function was given to us, we had infinity minus infinity, which is indeterminate. We did a little factoring, and now we have infinity times 0, still indeterminate, but still can't apply L'Hopital's rule to. So what I could do next is I could drop one of these into a denominator as its reciprocal. So I'm going to go ahead and go with the x. I'm going to drop that into the denominator, rewrite this as limit as x is approaching infinity of e to the 1 over x minus 1 divided by 1 over x. And notice what happens now. When I evaluate this, I'm going to get 1 minus 1, which is 0 on the top, and then 1 divided by infinity is 0 on the bottom. And so I've got 0 over 0. And now I'm in the form where I can apply L'Hopital's rule. So I've got to go through that process until I get it into a quotient that is of the indeterminate form, 0 over 0 or infinity over infinity. Once there, then I can apply L'Hopital's rule. L'Hopital's rule says that this is going to be the limit of the derivative of the top. So the derivative of e to the 1 over x is e to the 1 over x times the derivative of 1 over x, which is negative 1 over x squared, minus 0. And then the derivative of the bottom is going to be a minus 1 over x squared. And notice by doing that, I end up with those two common factors that can cancel. This is now just the limit as x is approaching infinity of e to the 1 over x, because the other two factors have canceled, and that can be evaluated as x approaches infinity, 1 over x goes to 0, so that's e to the 0, which is 1, and we have our answer for the limit. Okay. So our process is first to identify if we have an indeterminate form, second to manipulate it into the indeterminate form 0 over 0 or infinity over infinity if necessary, and then apply L'Hopital's rule. So we'll leave off this video just summarizing indeterminate forms thus far. We have one more round of indeterminate forms to go, but thus far we've got 0 over 0, we've got infinity over infinity, we've got infinity minus infinity, and we've got 0 times infinity. These two we have to use some strategy before applying L'Hopital's rule. We have to use some strategy to get these into one of these two forms. These are the two forms where L'Hopital's rule is applicable. So if you have 0 over 0 or over infinity with a quotient, the limit of a quotient, then you can apply L'Hopital's rule. Okay, we will come back on the last video with the last set of indeterminate forms. So we've got 4 so far, and we're going to add a few more.